Okay, this will be the lecture for Chapter 9. We'll be talking about gravity. And what we're going to start off with is it turns out that Newton didn't discover gravity, but he did discover that it was universal. So we'll talk about his universal law of gravity as well as the gravitational constant. We'll talk about how gravity depends on how close or far away objects are. And we'll talk a little bit more about weight and what it means to be weightless. And lastly, we'll finish off with ocean tides and how that's related to gravity. Now, legend kind of had it that Isaac Newton was sitting underneath an apple tree and an apple hit him on the head, and that's when he discovered gravity. And actually, he was not the first to discover gravity. They knew about that well before Isaac Newton, but he's the one that discovered it was universal. And just kind of legend has it is Isaac Newton was sitting underneath a tree and he realized that the earth pulls on the apple and the apple pulls on the earth, and also maybe the moon also pulls on the apple. So he kind of discovered that any objects with mass are going to exert a force on each other. Prior to Galileo, people thought that we had celestial laws, which were laws that governed planets and stars, and then laws that applied on Earth. And Isaac Newton was the fellow that realized no. The same set of laws must apply to both celestial and terrestrial objects. And so he kind of realized that an apple is going to pull on the earth, and the earth is going to pull on the apple. The sun is going to pull on the earth, and the earth is going to pull on the sun. And Isaac Newton came up with this universal law of gravity, and he said everything is going to pull on anything else as long as they each have mass. Something that's kind of interesting is you see the word pulls on. We're never going to see the word push, at least not with gravity. So things are always going to pull, they're not going to push. So there's always going to be an attractive force. So every body is going to attract every other body with a force that depends on their masses. We're going to multiply their masses together, and we're going to divide by the square of the distance separating them. Now, if that last slide was a bit of a mouthful, maybe we could say that the force is going to depend on the product of the masses, so the mass of two objects. So here I'm going to have object 1, and here I'm going to have object 2. And this guy's going to have some mass, this guy's going to have some mass, and they're going to be separated by some distance. And we're going to multiply the masses and divide by the distance, and be very careful, that's a distance squared. And this is kind of a constant of proportionality. We'll talk about that constant on the next slide. And essentially what this guy says is, okay, the larger these masses are, M1 and M2, then the larger the force of attraction. So as this guy goes up, or as this guy goes up, then the force of attraction is also going to go up. And as the distance of separation were to increase, then we're dividing by a larger number, so the force is going to go down. Now we can kind of get rid of that little squiggle on the previous slide, which was saying of proportionality, and we can introduce this constant of proportionality right there, which is just going to be a gravitational constant g, which has this value right here, and that's a really small number if you notice. It turns out that gravity is actually one of the weakest of the 4 known fundamental forces that we have, and we'll talk about the other forces in Physics 102. And essentially what we can do is we can calculate the force of any two objects. So let me just pick two objects. I'm going to have a 100 kilogram object and a 50 kilogram object, and I'm going to separate these guys by something pretty small, maybe half of a meter. Let's calculate the force on these guys. So it's going to be that constant, 6.67 times 10 to the negative 11th, multiplied by the mass of the first, multiplied by the mass of the second, divided by the distance squared, 0.5 squared. And I get that force to be equal to 1.3 times 10 to the negative 6 newtons. And that's a really small force, right? 10 to the minus 6 is a small number. So what this kind of means is as long as we're talking about regular, sized objects, 100 kilograms and 50 kilograms, the force of gravity is relatively small. Once we start talking about more massive things like the Earth, 10 to the 24th kilograms, right? As this mass goes up, then the force also goes up. Then we can start talking about real forces. We need to be talking about big things like the Earth, the Sun, the Moon, and so on and so forth. One thing to kind of keep in mind is that these are action-reaction pairs. So this right here is going to be that force, and this right here is going to be that force. So each of these guys are going to be attracting the other object. Let's just kind of explore, the distance aspect of it. The force kind of went like 1 divided by the distance squared. And what that really kind of says is if you have two objects and you increase the distance of separation, you're dividing by a larger number, so the force is going to go down, and it's not going to linearly go down, it's going to go down like distance squared. And the funny thing is even at very large distances, the force is going to get really, really, really close to zero, but it's never going to quite reach zero. So what this kind of means is if we took an apple and we had it at the I had it right here, and it had a weight of a Newton. If I went out to twice the diameter of the Earth, then the force, which is proportional to 1 divided by distance squared, is actually going to go down like 1 divided by 2 squared, so it's going to go down to about 1/4. You can kind of see that this gravitational force is going to drop off quite rapidly, and as it gets really, 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 really far away, the force is nearly zero, but it's never going to be exactly zero. Just to kind of make sure you're staying awake, the force of gravity is going to depend on what? I hope that you're guessing A, the mass and the distance apart. Now let's just get a little bit of practice, try to solve this one on your own. Okay, so if we have two planets and the mass of both of them are somehow doubled, then what's the force of gravity between them? Well, the force is going to be equal to big G times the mass of the first. We don't know what it is, let's just call it 1. Multiplied by the mass of the second, we don't know what it is, let's just call it 1. And let's divide by the distance squared, we don't know what it is, let's call it 1. So the force is just going to be G. Now if we were to double both of those guys, so double the first, double the second, distance squared is still the same, and we're left with 4G, so we would expect it to quadruple. If the mass of one planet was somehow doubled and the other one remained the same, then you could probably convince yourself that the force should double as well. Now, I want to talk a little bit about weight and gravity, and weight is always going to be equal to mass multiplied by gravity, and what we're kind of figuring out is that this force is actually going to get smaller as we move further and further and further away, so I've kind of been lying to you when I said this earlier. But when we think about what the weight we feel, that's actually going to be the force that the floor pushes up on us with. And I have some kind of examples about how we can mess around with that right here, and I'll kind of talk to them as we get to those guys. When we think about weightlessness, then it just turns out that there is no support force, and it's kind of like being in a free fall. So think of Wile E. Coyote, falling down a cliff. He's going to feel weightless. Astronauts in orbit are there's no net force, or there is some forces on them, right? We still have the Earth sitting over here kind of pulling on this guy. It's just he doesn't have anything to essentially push up against, and he's essentially kind of falling around the Earth constantly like that and constantly missing the Earth. So it's not like there's no force on him, it's just there's nothing for him to support himself on. So let's just kind of think about what we perceive our weight to be. If we're in an elevator and it's not moving, then we're going to perceive our weight to be just our normal weight. Or if the speed was a constant, then we would actually feel just our normal weight. However, as the elevator started to accelerate upwards, then what's kind of happening is this floor right here is ramming into the girl, essentially pushing her up, and she has inertia. She doesn't want to accelerate upwards, so if she was standing on a scale, it would read something larger than her normal weight because the scale's being rammed into her. If the elevator was kind of descending and accelerating as it did it, then the opposite is going to be true. It's kind of falling away from her, so it's going to be less than her normal weight. And if the cable were to break, then she wouldn't have anything to push up against, so she would be weightless, and she doesn't look too awful happy about that either, and it would read 0 weight. So just to make sure you are awake, as an elevator accelerates upwards, your weight reading on a scale should be greater. As it accelerates downwards, the weight reading is going to be less. And if the cable breaks, then the weight reading is going to be 0. And last but not least, if you weigh yourself in an elevator, you're going to weigh more when the elevator, now you might be tempted to pick that one, but that is not the right answer, moves upwards, and it doesn't really say it, but it is not accelerating. This one right here is accelerating, so this is the correct answer. Remember, the elevator can be moving upwards, but it's not until it starts jerking the girl upwards. It's not until it's accelerating. So this is not the right choice, not the right choice, and definitely not the right choice. So let's kind of finish off the chapter by talking a little bit about ocean tides. We know that there are going to be low tides and high tides, and a low tide is exactly what it looks like. The water is kind of low relative to the pier, and right here it's going to be relatively high relative to the pier. Let's kind of talk about what causes that. Well, we know that celestial bodies are going to pull on each other. So here the Earth is going to pull on the Moon, and the Moon is going to pull on the Earth with equal but opposite forces. But if you think about it, the force right here is going to be larger than the force right there, simply because it's closer. And what, 70% of the Earth's surface is covered with water, so the water is going to essentially bulge. And essentially these guys are going to go around each other every 12 hours. So we're going to get high tides right here and here about every 12 hours, and low tides there and there, and this water is just going to slosh back and forth, back and forth, back and forth. Two kind of fun and somewhat nifty types of tides is going to be when we have the sun and the moon lining up, in which case the Earth is going to feel a force due to the moon, and then it's going to feel a force due to the sun. So force due to the moon, force due to the sun, and obviously two forces means a lot of bulge. So these are called spring tides, which are going to be very high tides. And kind of an opposite example is going to be when the moon is up there, so the force due to the moon is right there, and all we have is some teeny tiny force due to the sun. And not surprisingly, these are going to be really, really low tides called neap tides, so very low tides. And again, what causes them is just the orientation of the sun and the moon.